Our universe is flowing toward a place that should not exist. Across unimaginable distances, thousands of galaxy clusters are streaming together like a cosmic river, pulled by a force we cannot see. This is the cosmic dark flow, a profound mystery that defies everything we know about the cosmos. By the end of this journey, you will understand the 25 deepest puzzles this phenomenon has unleashed, from shattered scientific principles to the possibility of other universes tugging at our own. We will investigate why this motion suggests something colossal lurks beyond the edge of everything we can observe, and question whether our entire cosmic story is incomplete. What does it truly mean to discover that the universe might have a direction it prefers? The first and most foundational mystery is the motion itself. A team of astronomers was studying the subtle, ancient light from the cosmic microwave background, the afterglow of the Big Bang, using data from the Wilkinson Microwave Anisotropy probe. They were not looking for a cosmic current, they were mapping the faintest ripples in the infant universe. What they found, however, was not a relic of the past but a signal from the present, imprinted upon that ancient light. Hundreds of massive galaxy clusters, each containing thousands of galaxies, were all moving together. They were streaming at a staggering speed of roughly 600 kilometers per second toward a single patch of the sky, a direction astronomers call the Centaurus and Hydra constellations. This was not a gentle drift, it was a determined, coordinated flow. The sheer scale of it is what shattered expectations. These clusters are not neighbors. They are scattered across billions of light years, separated by vast cosmic voids. According to our bedrock theory of the cosmos, the lambda CDM model, the universe should have no preferred direction on such immense scales. After the explosive uniformity of the Big Bang, the motion of matter should be random, isotropic, like the scattered pieces of a perfectly symmetrical explosion. The dark flow is a stark contradiction. It is a river of galaxies wide as the observable universe itself, all flowing downstream toward a destination we cannot see. This coherent motion suggests every rule we have written about cosmic structure might be missing a crucial line, a line that points toward something immense and invisible, pulling from beyond the edge of everything we know. That coordinated river of galaxies points to a single, unsettling conclusion. The force pulling them must originate from beyond the cosmic horizon. This is the second and perhaps most profound mystery. What truly lies beyond the edge of everything we can see? Our observable universe is a bubble, limited not by a physical wall, but by the speed of light and the age of the cosmos. We can only see objects whose light has had time, in the nearly 14 billion years since the Big Bang, to travel across the void and reach our telescopes. Everything outside that bubble, beyond that horizon, is fundamentally and permanently hidden from us. It is the ultimate terra incognita on the cosmic map. Yet the dark flow behaves as if something out there is tugging on the fabric of space within our bubble. Imagine standing in a vast, foggy field where you can only see a few hundred meters in any direction. Everything within your view is still, but then you notice all the leaves on the ground, all the way to the fog's edge, are sliding in the same direction, as if pulled by a colossal, invisible magnet lying somewhere out in the impenetrable mist. That is our predicament. The most straightforward explanation is gravitational. An unimaginably vast concentration of mass, a cosmic superstructure on a scale that dwarfs anything we have catalogued, could be exerting its pull from beyond the horizon. This would not be a mere cluster of galaxies, but something primordial and staggering, perhaps a relic from the chaotic moments before our Big Bang, or a titanic knot of space-time from an entirely different epoch. Even more radical is the multiverse implication. The flow could be the gravitational fingerprint of a neighboring universe, a separate cosmic bubble floating in a wider multiverse sea, brushing against our own. Its immense mass, though forever unseen, would warp the space around our universe, creating the current we observe. This transforms the dark flow from a curious anomaly into a potential window, a tiny crack in the wall of our reality through which we might infer the existence of an entirely alien cosmos. It forces us to confront a humbling and exhilarating question. Are we merely detecting the shadow of a neighbor we will never meet? This coordinated motion does more than hint at hidden masses. It directly confronts a pillar of modern cosmology, our third great mystery. For over a century, scientists have operated under a profound assumption known as the cosmological principle. It states that on the very largest scales, the universe is both homogeneous and isotropic. Homogeneous means the cosmos is roughly the same everywhere, a uniform soup of galaxies and dark matter. Isotropic means it looks the same in every direction, with no special place and no preferred axis. This principle is not just a philosophical idea. It is the bedrock upon which we built our entire understanding of cosmic evolution, from the equations of general relativity that describe the Big Bang to our maps of dark energy. The dark flow is a stark, screaming anomaly to isotropy. A preferred direction is exactly what the principle says should not exist. Think of it like this. If you stir a cup of coffee thoroughly and let it settle, the liquid becomes uniform. Drop in a single grain of sugar and it will sink straight down, pulled by gravity in one clear direction. That sinking grain reveals the cup has a top and a bottom, a preferred orientation. Before the stir, the coffee was isotropic. After, it was not. The dark flow is our cosmic sugar grain. It suggests that on the grandest canvas imaginable, the universe might have a top and a bottom, a subtle gradient or tilt woven into the fabric of space itself. The ramifications of this are staggering. If the cosmological principle cracks, the foundations of our models begin to tremble. Our calculations for the amount of dark matter and dark energy, our predictions for the ultimate fate of the cosmos, even our confident story of the Big Bang, all rely on that assumption of large-scale uniformity. A universe with a preferred direction is a different universe altogether, one where the rules might change depending on which way you look. We would be forced to ask, is this flow a local oddity in our cosmic neighborhood, or is it a fundamental feature of the entire cosmos? Answering that could mean rewriting the textbook on reality. Such a monumental claim demands monumental proof, and here we reach the fourth great mystery. Is the dark flow a real feature of our universe, or is it a grand illusion born from the limits of our instruments? This is not a simple disagreement. It is a deep and ongoing debate at the very frontier of cosmology, a tug of war over the meaning of a whisper heard across 14 billion years. Skeptics argue compellingly that the signal could be a subtle artifact, a mirage created by our own process of observation. One primary suspect is something called the kinetic Sunyaev-Zeldovich effect. This is a complex phenomenon where the hot gas within galaxy clusters subtly distorts the cosmic microwave background light in a way that can mimic motion. If we have not perfectly modeled and subtracted all these local distortions from our data, they could leave behind a false pattern, a ghostly current that is not really there. Other potential culprits include instrumental noise, the immense challenge of mapping such faint signals, or even our incomplete understanding of how galaxy clusters themselves move on slightly smaller scales. For some scientists, the simplest explanation is that we are seeing the collective result of many smaller, local gravitational pulls, not one giant tug from beyond. They contend that our models of large-scale structure, while impressive, are not yet perfect, and the dark flow could simply vanish as our maps become more precise. On the other side of this cosmic courtroom are the investigators who believe the signal is real and profound. Subsequent studies, particularly those using the exquisite data from the European Space Agency's Planck satellite, have reported detecting similar bulk flows, though sometimes at different scales or speeds. Some analyses of X-ray observations from galaxy clusters have also been interpreted as supporting evidence for coherent motion. These teams argue they have carefully accounted for the known foreground effects and instrumental uncertainties, and the stubborn signal remain. The debate, therefore, is not just about data. It is a mystery of scientific methodology itself. How do you verify a signal that exists at the very threshold of detection, a ripple so faint it is barely distinguishable from the sea of cosmic noise? It is a struggle to interpret a signature from the edge of reality, using tools that are themselves being refined in real time. This tension is the engine of discovery. It forces every new observation, every fresh analysis to be a ruthless test. The dark flow hangs in this precarious balance, not yet confirmed as a fundamental feature of the cosmos, but refusing to be dismissed as a mere fluke. Its very persistence as a question compels us to look deeper, to build better telescopes, and to question our assumptions more fiercely than ever before. The debate over its reality leads us to a fifth, more tangible mystery, one that hits closer to home. We are already being pulled. Our own Milky Way galaxy, along with our entire local group of galaxies, is caught in a vast cosmic current, streaming toward a mysterious region of space about 250 million light-years away. Astronomers call this the Great Attractor. It is a gravitational focal point so immense that it warps the motion of hundreds of thousands of galaxies, including our own. Yet for decades, its true nature was hidden from our view, lying in the obscured zone behind the dense stars and dust of our own galaxy's central plane. We now believe it is not a single monstrous object, but a colossal confluence of mass, a supercluster of galaxies known as the Norma cluster, anchored by a dense core of dark matter. It is a local, though still immense, gravitational pothole in the cosmic highway. The dark flow is something else entirely. If the Great Attractor is a pothole, the dark flow is the slope of the entire continent. The scale is incomprehensibly larger. The dark flow encompasses galaxy clusters billions of light-years apart, suggesting a source of gravity that lies not 250 million light-years away, but potentially far beyond the observable universe itself. This raises a profound and layered question. Are these two phenomena separate, or are they connected? Could the dark flow be the Great Attractor's unimaginably bigger brother? One tantalizing possibility is a cosmic hierarchy of influence. Our local galaxies fall toward the Great Attractor. But what if the Great Attractor itself, and every other massive structure we see, is also in motion, caught in an even grander current toward something beyond the horizon? We would be witnessing gravitational influence on nested scales, like a stream feeding into a river which itself flows into an ocean. The dark flow would be that ultimate ocean current. This idea transforms our cosmic map from a static snapshot into a dynamic, flowing system with depths we are only beginning to fathom. It suggests that the forces shaping our corner of the universe might be mere echoes of a far more powerful tug from the true depths of reality. The mystery deepens. Are we seeing two separate puzzles, or just different pieces of the same, infinitely larger one? The possibility of a cosmic tug of war brings us directly to our sixth mystery, one that implicates the most powerful yet invisible forces in the universe. How does the dark flow relate to dark matter and dark energy? These two shadowy components dominate the cosmos, making up over 95% of everything that exists, yet we know almost nothing about their true nature. Dark matter is the cosmic glue, its gravity holding galaxies together. Dark energy is the cosmic repulsion, accelerating the expansion of the universe. The dark flow, a vast directional motion, seems to insert a third, disruptive actor onto this stage. Could it be a manifestation of something wrong with our understanding of these dark components? One compelling theory suggests the flow might reveal an unevenness in dark energy itself. Our standard model treats dark energy as perfectly smooth, a uniform force permeating every cubic centimeter of space. But what if it isn't uniform? What if dark energy has subtle ripples, hills and valleys in its intensity across the cosmos? A vast region where dark energy is slightly weaker would feel a stronger gravitational pull from surrounding areas, creating a current of matter flowing into that low-pressure zone. The dark flow could be the signature of this cosmic gradient, a slow-motion rush into a valley of weaker repulsion. This would mean dark energy is not a static background force, but a dynamic field that can vary from place to place with profound consequences for the ultimate fate of the cosmos. Another possibility involves dark matter. We assume its only interaction is through gravity, but what if certain types of dark matter can exert or feel other, extremely long-range forces? These forces could create large-scale correlations in motion, orchestrating the synchronized flow of galaxy clusters across billions of light-years. The dark flow might then be a ghostly current within a dark matter ocean, revealing interactions in a hidden sector of reality. The most dramatic interpretation frames it as a literal tug of war across the void. On one side is the relentless push of dark energy, trying to stretch space and separate all structures. On the other side is the gravitational pull of an unfathomable mass beyond our horizon. The dark flow could be the visible sign that, in our region of the universe, the external pull is winning. It is as if our cosmic bubble is sliding down a gentle slope in the multiverse, dragged by a gravity so immense it can counteract the repulsive force that dominates everywhere else. This transforms the flow from a curious anomaly into a potential balancing scale, weighing the strength of dark energy against the gravitational influence of the truly unknown. Each of these ideas turns our fundamental assumptions inside out, suggesting that the dark flow is not just a problem of missing mass, but a clue that the dark universe itself is far more complex and textured than we ever dared to imagine. Perhaps the most breathtaking possibility is that the flow is not a pull at all, but a gentle shove from a passing stranger. This seventh mystery dares to ask a question that sounds like science fiction, yet is grounded in the mathematics of our most advanced theories. Could the dark flow be evidence of our universe brushing against another? To understand this, we must venture into the realm of the multiverse, specifically a concept called eternal inflation. This theory suggests our Big Bang was not a unique, singular event, but one of countless cosmic bubbles spontaneously inflating within an endless, seething sea of higher dimensional space. Each bubble is its own universe with its own laws of physics, forever expanding and floating in this greater void. Now, imagine two such bubbles, two separate universes drifting in this cosmic foam. If they pass close enough, they would not collide in a cataclysm of stars and planets. Their three-dimensional membranes or brains exist in a higher dimensional bulk. Their interaction would be through gravity alone, the one force thought to be able to leak between these separate realities. The gravitational field of a neighboring universe passing by in the hyperdimensional dark could exert a tidal force on our own cosmos. It would not tear our universe apart, but it could create a subtle, coherent drag on everything inside it, a vast, directional wake left by the passage of a cosmic ship in a sea we cannot perceive. The dark flow would be that wake. It is the ghostly imprint of a near miss with an alien reality, a gravitational whisper from a cosmos whose stars are made of particles we cannot imagine, governed by forces that would seem like magic. This idea emerges from brain cosmology, a framework born from string theory. In this view, our entire three-dimensional universe is a membrane, like a vast, impossibly thin sheet of reality, floating within a higher dimensional space. Other brains, other universes could be floating nearby. Their gravitational influence would stretch across the dimensional gap, potentially creating large-scale alignments and flows within our brain. The imagery is staggering. We are not isolated. We are sailing through a hyperdimensional ocean, and the current we feel might be the tide from a shore we can never see. This transforms the dark flow from an astronomical anomaly into a potential landmark, the first experimental hint of a reality beyond our own. It suggests our cosmos has neighbors, and we have just felt the breeze from an open window in a house we did not know existed. That gravitational whisper from another universe is not the only way to hear echoes from beyond. The eighth mystery asks if the dark flow is not a signal from a neighbor, but a relic from a parent. Could this cosmic river be a fossilized remnant, an imprint from a time before our own Big Bang? This idea challenges the most fundamental starting point of our story, that the universe and time itself began in a singular, hot, dense state. Some of the most ambitious theories in physics suggest otherwise. They propose a cosmos without a true beginning or end, but with cycles of death and rebirth on timescales that dwarf human comprehension. In one such vision, the conformal cyclic cosmology proposed by physicist Roger Penrose, our universe is not the first. It is merely the latest in an infinite series of cosmic eons. In this model, the distant future of one eon, a cold, empty expanse dominated by massless radiation, becomes mathematically identical to the hot, dense singularity of the next. Information in a highly scrambled form could cross this boundary. The large-scale structure of a previous universe might leave a faint statistical imprint on the next one, like a watermark on cosmic paper. The dark flow, with its vast, coherent direction, could be such an imprint. Its alignment might not point toward a place, but toward a moment, the final, asymmetric collapse or collision of the prior cosmic eon. It would be a cosmic arrow frozen in the fabric of our newborn universe, pointing back to an event in a reality that no longer exists. Other cyclic models, like those in certain string theory frameworks, imagine our three-dimensional universe as a membrane that periodically collides with another in a higher dimensional space. Each collision is a big bang, a rebirth. The momentum and orientation from one cycle could carry over to the next. If the previous cycle ended with our cosmic brain sliding in a particular direction, that directional momentum might have been baked into the very first moments of our new universe, manifesting billions of years later as the dark flow we observe today. This transforms the phenomenon from a spatial mystery into a temporal one. The flow is not something pulling us now, but a ghost of a prior now. It is a scar, a memory written into the geometry of space itself, a testament to a history we thought was forever erased by the fires of creation. To detect it would be to read a chapter from a book that was burned before our story even began, suggesting that our universe carries within it the silent, directional echo of its own ancestry. The sheer scale of the coordination defies our basic intuition of how the cosmos works. This is the ninth mystery, the puzzle of coherence over distances that should make such unity impossible. We are not talking about a local group of galaxies or even a single supercluster. The signal suggests thousands of massive galaxy clusters, separated by billions of light-years of near-empty void, are all streaming in concert. To grasp the absurdity, picture two rafts floating on a calm, vast ocean, separated by a distance greater than the entire Pacific. Now imagine they suddenly begin drifting in the exact same direction, at the exact same speed, as if connected by an invisible rope. According to the laws of physics as we understand them, that rope cannot exist. Gravity, the force that would orchestrate this motion, weakens dramatically with distance. For gravity to coordinate these clusters, the information to start moving the gravitational pull would need to travel from the source to the farthest cluster faster than light, or at least in a way that links them all instantly. But nothing, not even gravity, is supposed to travel faster than light. In the time since the Big Bang, there simply hasn't been enough time for a slow, creeping gravitational influence to organize matter across such an immense volume of space. The clusters are too far apart to have communicated the plan, so how can they all be following it? This forces us into strange and profound territory. One possibility is that the flow was not organized by a distant mass acting over time, but was imprinted at the very beginning. Think of the early universe not as a uniform explosion, but as a stretched fabric that already had a subtle tilt woven into its threads. In the first fleeting fractions of a second after the Big Bang, during a period called inflation, the entire observable universe was smaller than an atom. Any directional preference, any primordial velocity field, would have been locked in during that hyper-expansion and then stretched to cosmic proportions. The clusters are not being pulled now. They are simply coasting on momentum set in motion 14 billion years ago, like leaves frozen in an ice sheet that continue drifting in the same direction when the ice finally melts. This idea turns the dark flow from a present-day force into a fossil of the universe's first moment, a relic of an asymmetry born in the fire of creation itself. It means the cosmos might have had a preferred direction from its very first breath, a whisper of bias that has echoed through the eons to shape the motion of everything we see. But a fossil from the first moment or a whisper from another universe must first survive the most ruthless scrutiny of all. The 10th great mystery is not about the cosmos, but about our own perception. Could the dark flow be nothing more than a grand, systematic error? This is not a dismissal, but a deep and necessary dive into the profound technical challenges of measuring the universe itself. To detect the flow, astronomers use the cosmic microwave background as a universal reference frame, the stillest backdrop imaginable. They look for a subtle shift in its temperature caused by the motion of galaxy clusters through it, known as the kinetic Sunyaev-Zeldovich effect. The entire endeavor is an exercise in precision at the very limit of possibility. First, you must perfectly calibrate your celestial compass. The cosmic microwave background is not perfectly uniform. It has its own intrinsic ripples from the Big Bang. Separating these primordial wrinkles from the distortion caused by a cluster's motion is like trying to hear a single instrument tuning in a symphony hall while the entire orchestra is warming up. Then you must account for our own motion. The Earth orbits the Sun orbits the Milky Way, and our entire galaxy is barreling through space. This local velocity creates a massive dipole signal in the cosmic microwave background, a hot spot in one direction and a cold spot in the opposite direction. Before you can see any distant flow, you must subtract this overwhelming local signal with flawless accuracy. Any tiny miscalculation here imprints a false direction on the entire map. Next comes the galaxy clusters themselves. We do not measure the motion of the stars, but of the incredibly hot gas that fills the spaces between them. Modeling this atmosphere, its density, temperature, and distribution is extraordinarily complex. If our models are even slightly off, we could mistake a local turbulence within the cluster for a coherent motion of the entire structure. It is like trying to measure the drift of an iceberg by studying the ripples in a meltwater pool on its surface. Finally, there is the statistical gauntlet. The signal is incredibly faint, buried in a sea of noise from other astrophysical processes and the instruments themselves. Determining its significance is a monumental task. How many clusters show the signal? Is it consistent across different datasets? Could a random alignment of many smaller, unrelated motions conspire to look like a single, vast current? This is the core of the scientific battle. One team's careful subtraction is another team's overlooked artifact. The Planck satellite, with its exquisite sensitivity, provided data that both camps have used to argue their case. Some analyses of the Planck data found the signal persisted, while others, using different methods to handle foregrounds and noise, saw it vanish. This disagreement is not a failure. It is the sound of the scientific method grinding against the hardest problems. The dark flow exists in a twilight zone of cosmology, a place where the signal-to-noise ratio is so low that the line between discovery and delusion becomes perilously thin. To accept it, we must trust not just a number on a screen, but an entire chain of assumptions, corrections, and statistical models, each one a potential point of failure. This mystery forces a humbling admission. our window on the universe, for all its technological marvel, is still smudged, and the greatest challenge may be figuring out if the shadow we see on the glass is cast by a monster outside or is just the shape of our own thumb. The debate over systematic error forces scientists to seek a verdict from an independent witness. This is the 11th mystery, a live and unfolding drama in the scientific literature. The quest for independent confirmation has sent astronomers to the most extreme environments on Earth, building telescopes in the thin, dry air of the Chilean Atacama Desert and the frozen, pristine darkness of the South Pole. These instruments, like the Atacama Cosmology Telescope and the South Pole Telescope, are not looking at stars. They are tuned to the faint millimeter wave whispers of the cosmic microwave background, hunting for that same subtle distortion, the kinetic Sunyaev-Zeldovich effect, in hundreds more galaxy clusters. The goal is pure and simple: replicate the finding with a different instrument, a different team, and a different slice of the sky. If the signal is real, it should appear again. The results, however, have been a masterclass in scientific tension. Some analyses of this new data have indeed reported a bulk flow, a coherent motion on astonishing scales, seemingly bolstering the original claim. Other teams, looking at the exact same datasets but with different statistical methods or foreground cleaning techniques, have found the signal vanishes into noise. It is a conflict not of personalities but of profound technical interpretation. Meanwhile, a completely separate line of evidence has entered the courtroom. X-ray astronomers have turned their space-based observatories toward the hot gas within these same distant clusters. By studying the slight distortions in the X-ray glow caused by the cluster's motion through the intergalactic medium, they can infer a velocity. Some of these X-ray studies have also suggested peculiar, coherent motions among clusters, adding another curious piece to the puzzle. Yet, these results too are contested, with other researchers pointing to potential calibration issues or alternative explanations for the X-ray signatures. The truth, therefore, hangs in a precarious and exhilarating balance. We are witnessing the scientific process in its rawest form, a slow-motion detective story where the clue is a phantom and every new test seems to deepen the mystery rather than solve it. This is not failure, it is the hard, granular work of probing the absolute limits of our knowledge. The dark flow has become a cosmological litmus test, revealing just how challenging it is to measure the universe when the signal you seek is written in vanishingly faint ink at the very edge of the page. When a phenomenon defies every standard explanation, the doors of theoretical possibility swing wide open. The dark flow has done precisely that, unleashing a 12th and thrilling mystery, a theoretical Pandora's box filled with ideas that range from the elegantly revised to the wildly speculative. Confronted with a universe that seems to have a preferred direction, cosmologists have been forced to ask if the problem lies not in what is out there, but in the rules we have written here. Perhaps gravity itself behaves differently on the grandest scales. This idea is not entirely new. For decades, a minority of physicists have championed theories of modified gravity, like modified Newtonian dynamics, or MOND, to explain the rotation of galaxies without invoking dark matter. The dark flow reignites this debate on a cosmic scale. Could it be that Einstein's theory of general relativity, while spectacularly successful, needs a subtle tweak when applied to the fabric of the entire observable universe? A modified law of gravity could, in principle, generate large-scale flows without any hidden external mass. It would mean the river of galaxies is not being pulled, but is flowing downhill on a gentle slope created by the geometry of space-time itself, a geometry described by new equations. Another radical rethinking abandons the cosmological principle entirely. What if the universe is not smooth but profoundly lumpy on scales larger than we can see? Enter the giant void models. In these scenarios, our galaxy is not in an average place but sits in a relatively empty bubble, a vast cosmic underdensity hundreds of millions of light years across. Surrounding this void are the dense walls of the cosmic web. The gravitational pull from these immensely crowded regions outside our bubble could create a net tug in one direction, simulating a dark flow. We would be like a boat in the calm center of a giant whirlpool, feeling the current drag us toward the outer rim. Then there are the truly exotic constructs, relics from the early universe's violent birth. Cosmic strings are hypothetical defects in space-time, infinitesimally thin but unimaginably dense ribbons of energy left over from the phase transitions of the Big Bang. Think of them as cracks frozen in the fabric of reality, each possessing the mass of a galaxy compressed into a width smaller than an atom. A cosmic string stretching across the cosmos would warp space around it with immense gravitational force. If one existed in just the right orientation, it could act as a celestial guide rail, shepherding galaxy clusters along its length in a coherent stream. The dark flow could be the trail of breadcrumbs leading us to one of these primordial scars. Each of these theories is a desperate, creative attempt to explain the inexplicable within the confines of our observable universe. They reveal a profound truth about science at its frontier. When the map no longer matches the territory, we must consider redrawing the map, even if it means sketching in continents of theory we have never seen. The dark flow is not just a puzzle, it is an invitation to imagine a cosmos far stranger than the one in our textbooks. Their journey across the cosmos raises a question of ultimate destination. Where is this river of galaxies ultimately headed? This 13th mystery forces us to project the narrative billions, even trillions of years into the future, to consider the fate of the flowing clusters. If the source of the pull is a real, physical supermassive attractor lying beyond our horizon, what happens when or if these clusters ever reach it? The imagery is both majestic and terrifying. Imagine thousands of galaxy clusters, each containing hundreds of billions of stars, all converging on a single point in the cosmic dark. The gravitational tides would be unimaginable. Galaxies would be stretched and shredded, their stars flung into chaotic new orbits or consumed by the supermassive black holes at their hearts, which would themselves begin a slow, spiraling dance of merger and destruction. Over eons, this colossal pile-up could forge a single, monstrous structure, a hypercluster of such staggering mass and density it would defy all current categories. It would be a gravitational titan, a knot in space-time so tight it might become its own distinct cosmic entity, perhaps even seeding the birth of a new universe in some far future cycle. Yet, this dramatic vision hinges on a critical and sobering caveat: time and expansion. The dark flow speed, while immense by human standards, is a crawl on the cosmic stage. At roughly 600 kilometers per second, a cluster would take over 1 trillion years to cross a single billion light years. Meanwhile, dark energy is accelerating the expansion of the universe itself, stretching the very space between the clusters and their destination. This creates a cosmic race between the pull of gravity and the push of expansion. It is entirely possible that for many of these clusters, the finish line is receding faster than they can approach it. Their journey would then be eternal and futile, a forever pilgrimage toward a shore they can never reach. They would flow forever like ghosts on an endless river, destined to watch their goal fade into the infinite distance as the universe grows cold and dark around them. This duality captures the profound melancholy and scale of the cosmos. The dark flow may not be a story with a climax, but an endless procession, a direction without a destination, reminding us that in the grand theater of the universe, even the most powerful currents might lead only to an everlasting voyage. That endless voyage may have a landmark, a strange and frigid patch of sky that could be its point of origin. This 14th mystery asks if the dark flow is connected to another legendary cosmic anomaly, the cold spot in the cosmic microwave background. The cosmic microwave background is not perfectly smooth. It has tiny temperature variations, hot and cold patches that are the seeds of all future structure. But one cold region in the constellation Eridanus is different. It is far larger and significantly colder than our standard models can easily explain. It is a cosmic bruise, a blemish on the face of the infant universe that has puzzled astronomers for years. Some scientists now propose a startling link. Could the dark flow and the cold spot be two different symptoms of the same colossal event? One leading theory is the supervoid hypothesis. Imagine a region of space, billions of light years across, that is not just empty but profoundly, unnaturally empty. It is a cosmic desert on a staggering scale, a void so vast it defies the typical sponge-like structure of the universe. If our galaxy sat on the near side of such a void, the gravitational effect would be twofold. First, as light from the cosmic microwave background travels through this underdense region, it loses a tiny amount of energy climbing out of the void's weak gravitational pull. This process, called the integrated Sachs-Wolf effect, would make that part of the sky appear colder, creating the cold spot. Second, the immense mass of the denser universe surrounding this void would exert a gravitational pull on everything on our side, including our galaxy and distant clusters, drawing them toward the overdense wall. This could create a bulk flow in that exact direction. In this scenario, the cold spot is the shadow of the void, and the dark flow is the current it generates. We would be witnessing two faces of a single, unimaginably large cosmic structure, but there is an even more radical connection. Both anomalies could be signatures of a collision with another universe. In the brain cosmology framework, if our universe grazed another in the higher dimensional bulk, the impact would have sent shockwaves through the fabric of our reality. The collision zone itself might appear as a giant cold spot in the cosmic microwave background, a scar from the contact, and the gravitational wake from that passing universe could have set our entire cosmic neighborhood drifting, creating the persistent dark flow we observe today. The cold spot would be the point of impact, and the dark flow would be the direction of the shove. This idea weaves two of cosmology's greatest puzzles into a single, breathtaking narrative of inter-universal contact. It suggests we are not just looking at random statistical flukes, but at the scattered evidence of one titanic event, like finding matching pieces of shrapnel from the same explosion embedded in different parts of a battlefield. The alignment is tantalizing, though not yet proven. Some studies have searched for a supervoid in the direction of the cold spot and found evidence of underdensities, but nothing yet on the colossal scale required to explain both anomalies. The search continues and the link remains speculative, yet the very possibility transforms our investigation. We are no longer chasing separate ghosts. We are following a single trail of clues that hints at a disturbance so vast it left its mark on both the ancient light of creation and the present-day motion of galaxies. Could it be that by solving one of these mysteries, we automatically unravel the other? The possibility of a single, titanic event linking the cold spot and the dark flow forces a profound shift in perspective. Beyond the equations and data lies a 15th and deeply human mystery, one that asks not how the universe works, but what its structure means for our place within it. For centuries, we have viewed the cosmos as an island, the observable universe with its billions of galaxies and its cosmic horizon was the totality of our reality, the ultimate stage upon which the grand drama of existence played out. We were the audience in a self-contained theater. The dark flow shatters that comforting illusion. If we are being pulled by something beyond our horizon, then our island is not an island at all. It is a province, a neighborhood, a single piece of a puzzle so vast we cannot see its edges. Our universe becomes less of a whole and more of a part. This is a philosophical tremor as significant as the Copernican revolution, which moved Earth from the center of the solar system. Now our entire cosmic home, everything we can ever see or touch, might be displaced from any central privileged position. We are not just adrift in space, we are adrift in a metacosmos whose true geography is forever hidden. This realization injects a powerful dose of cosmic humility. All our theories, our maps of dark matter and dark energy, our confident timeline from the Big Bang to the present, they are based on a sample of one. We have been studying a single room and trying to deduce the blueprint for the entire mansion, unaware that a wind from an open window in a distant corridor is making the curtains in our room flutter. The dark flow is that flutter. It suggests the forces that shape our local reality may be set by conditions outside it, in realms that are, by definition, unknowable. Our cosmic story becomes a local history, perhaps with little bearing on the broader narrative of whatever exists beyond. This challenges the very notion of a theory of everything for our universe. Can you have a complete theory for a system that is not closed, for an island that is constantly being tugged by tides from an unseen ocean? It forces scientists to confront the limits of knowledge itself, to accept that some questions about our own cosmos may have answers that lie forever out of reach, locked beyond the ultimate horizon. Yet within that humility lies a breathtaking expansion of possibility. We are no longer alone. The cosmos is not a solitary, expanding bubble in an eternal void. It has neighbors or a parent, or exists within a structure of unimaginable complexity. This transforms our existential loneliness into a strange, new form of cosmic connection. We are part of something larger, even if we can never see it, touch it, or fully understand it. The awe this inspires is not of insignificance, but of participation. We are witnesses to a shadow on the wall of our cave, a hint that the world outside is vaster and more wondrous than we ever dreamed. The dark flow, then, is more than a puzzle for astronomers. It is an invitation to reimagine reality, to accept that our home is both finite and part of an infinite mystery, and to find a profound wonder in the simple, haunting fact that the universe seems to have a direction it prefers to go. The river of galaxies is not the only invisible force that could shape the cosmos. While gravity dominates our cosmic models, there exists another, more subtle power that might weave through the vast voids between clusters. This 16th mystery asks if we have overlooked the influence of magnetism itself on the grandest stage of all. Could primordial magnetic fields, threads of force left over from the universe's infancy, be the hidden hand guiding the dark flow? Unlike the magnetic fields we know from planets or stars, these would be relics of the first moments after the Big Bang, stretched by cosmic expansion to span hundreds of millions of light years. They would form a faint, fossilized web of energy permeating all of space. In this scenario, the hot, ionized gas that fills galaxy clusters is not just a passive passenger. It is a plasma, a sea of charged particles, and charged particles, as they move through a magnetic field, feel a force. A vast, coherent magnetic field aligned across the cosmos could gently shepherd this ionized gas, imparting a subtle directional preference to the entire cluster's motion. The clusters would not be pulled by gravity from beyond the horizon, but nudged by an immense cosmic magnetic current. This would mean the dark flow is not a gravitational mystery, but an electromagnetic one, a sign that the universe's magnetic skeleton is far more extensive and organized than we ever suspected. Detecting such fields, however, is a monumental challenge. Their signal is incredibly faint, buried in the polarized light of the cosmic microwave background and the diffuse radio glow between galaxies. Astronomers search for telltale twists in the polarization of ancient light or subtle distortions in the radio waves from distant quasars, looking for the imprint of these magnetic giants. The question is whether these fields could be strong enough and coherent enough over such immense distances to orchestrate the motion of thousands of clusters. It pushes the science of magnetohydrodynamics, which studies how magnetic fields and plasmas interact, to its absolute limit. Could the collective effect of many smaller, tangled fields add up to a large-scale push? Or is this a beautiful idea that simply lacks the necessary force? The investigation continues, a quiet parallel search for a different kind of cosmic whisper. It reminds us that our universe is governed by a symphony of forces, and while we have been listening intently for the deep bass of gravity, we may have missed the higher, more delicate notes of magnetism playing a crucial part in the movement of everything we see. Magnets and gravity may not be the only forces at play. The 17th mystery pushes us into the most fundamental frontier of physics, where the very fabric of space and time is woven from threads we cannot see. The dark flow could be more than an astronomical oddity. It might be our first real-world test for a theory of quantum gravity. For a century, physics has been split into two magnificent but incompatible kingdoms. Quantum mechanics rules the realm of the very small, where particles are probabilities and reality is fuzzy. General relativity governs the vast cosmos, where mass bends the smooth, continuous fabric of space-time. Unifying these two frameworks into a single theory of quantum gravity is the greatest unsolved problem in fundamental physics. The contenders, like string theory and loop quantum gravity, are breathtakingly elegant but notoriously difficult to test. They live in the domain of extreme energies, the Planck scale, far beyond the reach of any particle accelerator we could ever build. Their predictions seem locked away in the first moments of the Big Bang or in the hearts of black holes. This is where the dark flow enters, not as a distraction but as a potential key. Some versions of these quantum gravity theories suggest that the infant universe was not perfectly smooth. The fabric of space-time itself, when viewed at the quantum level, might have a granular texture like the pixels on a screen. As the universe inflated from a quantum seed, this microscopic graininess could have been stretched to cosmic proportions, imprinting a subtle but persistent directionality on the expansion. The dark flow could be the macroscopic echo of that quantum grain, a fossilized direction frozen into the geometry of everything. Other ideas propose that the laws of physics themselves were not set in stone at the beginning. In some multiverse or bouncing cosmology models, the transition from a prior state into our Big Bang could have selected a preferred axis, a kind of cosmic spin inherited from quantum processes in a parent universe. The flow would be the lingering momentum from that quantum leap into existence. If either of these connections holds, then the dark flow ceases to be merely a problem for cosmologists. It becomes a rare and precious observational clue for the theorists trying to build a complete description of reality. Solving its origin would not just tell us why galaxies are moving, it would force us to choose between competing visions of quantum gravity. Does the data better fit a universe born from vibrating strings or one built from woven loops of space? The dark flow's specific properties, its scale, its coherence, its exact alignment, could act as a fingerprint matching the unique predictions of one theory over another. Imagine trying to understand the properties of water by only studying individual molecules. It is nearly impossible. But if you see a river flowing, you instantly understand viscosity, pressure, and current. The dark flow is that river. It is a colossal, emergent phenomenon that might let us infer the nature of the quantum grains that make up the banks and bed of space-time itself. It offers a way to test the untestable, to bring the abstract mathematics of the Planck scale down to the human scale of observation. The mystery thus ascends to a new level of significance. We are no longer just mapping the universe. We might be reading the first lines of its ultimate operating manual. These whispers from the quantum realm were captured by two of humanity's most extraordinary eyes on the sky. The 18th mystery belongs not to the cosmos, but to the machines we built to listen to it. The dark flow's story is inseparable from the instrumental legacy of the Wilkinson microwave anisotropy probe and the Planck satellite. These were not ordinary telescopes, they were time machines exquisitely tuned to hear the faintest echo of creation, the cosmic microwave background. Their primary mission was to map the temperature of this ancient light in microscopic detail, to photograph the newborn universe. To do this, they carried instruments of almost unbelievable sensitivity. WMAP, launched in 2001, used a set of differential microwave radiometers. These devices did not measure absolute temperature. Instead, they compared the heat from 2 points in the sky, separated by a specific angle, searching for the tiniest differences between them, differences as small as a millionth of a degree. This method allowed it to filter out local noise and build an exquisitely precise map of the primordial hot and cold spots. Planck, launched in 2009, was even more advanced. It carried two revolutionary instruments, the low-frequency instrument and the high-frequency instrument. Together, they scanned the sky across 9 distinct frequency bands, from radio waves to the far infrared. This multi-frequency vision was crucial. It allowed scientists to peel away foreground contamination from our own galaxy, the dust and synchrotron radiation that obscures the pristine cosmic signal, like removing layers of static from a distant radio broadcast. It was within this cleaned, perfect map of the infant universe that astronomers found the anomaly. They were looking for the kinetic Sunyaev-Zeldovich effect. This occurs when the hot, electron-filled gas of a galaxy cluster moves through the sea of cosmic microwave background photons. As these photons scatter off the fast-moving electrons, their energy is subtly shifted, creating a tiny, specific distortion in the temperature of the background light in that direction. Detecting this is an act of precision bordering on the impossible. You must measure a temperature shift of just a few millionths of a degree, superimposed on a signal that is itself only 2.7 degrees above absolute zero, and do it for thousands of clusters scattered across the sky. WMAP provided the first tantalizing hint. Planck, with its superior sensitivity and frequency coverage, delivered the data that turned the hint into a full-blown cosmological crisis. These missions, designed to look back to the very beginning, inadvertently opened a window to something potentially beyond the end of our observable reality. They were built to chart the origins of our cosmic home, and instead they may have found the door to a neighbor's house. Every debate, every radical theory about the dark flow begins with the pristine day to these silent sentinels beamed back to Earth. Their legacy is a profound reminder that the greatest discoveries are often not the answers we seek, but the better questions we learn to ask. The pristine data from those satellites does not speak for itself. It whispers, and we must decide if that whisper is a secret or just the wind. This 19th mystery plunges us into the high-stakes numbers game of cosmology, a statistical battle where the fate of entire theories rests on a single question. Is the dark flow a real signal, or is it just an extraordinary stroke of cosmic noise? To answer this, scientists do not simply look at a map and point. They build entire fake universes by the thousands. They employ a powerful technique called Monte Carlo simulation, named after the famous casino because it relies on the roll of digital dice. Here is how the battle is fought. First, you take our best model of the universe, the standard lambda CDM model, with its smooth dark energy and randomly distributed dark matter. You program this model into a supercomputer and tell it to create a mock cosmos, a digital twin of our universe as it should be, with no external pulls or preferred directions. Then you simulate an observer in that fake universe, point a virtual telescope at the virtual sky, and measure the motions of its virtual galaxy clusters. You record the result. Now you do it again and again, 10,000 times, 100,000 times. Each simulation is a roll of the cosmic dice, generating a universe under the known rules. This creates a vast library of what random, standard universes look like. It tells you what kind of bulk flows can arise purely by chance from the ordinary clumping of matter and the vagaries of cosmic structure formation. Next, you take your real, observed measurement, the speed and coherence of the alleged dark flow from the actual Planck or WMAP data. You walk into your library of 100,000 simulated universes and ask, how many of these random, standard universes produced a flow as strong, as coherent, and as large-scale as the one we seem to see? If only 5 out of 100,000 mock universes show something similar, that is a very rare event. Scientists translate this rarity into a p-value, a probability that the signal could be a fluke. A low p-value, say 1 in 10,000, suggests the signal is significant. It means the standard model struggles to explain what we see, and something else, something new, might be required. This is the threshold of discovery, but the battle is far from simple. The opposing side scrutinizes every step. Did the simulations accurately capture all the complexities of galaxy cluster physics? Did the analysis of the real data properly account for every possible foreground contaminant? Could there be a subtle bias in how the clusters were selected for the study? Skeptics run their own simulations with different assumptions or statistical methods, and sometimes find that the observed flow falls comfortably within the range of expected random fluctuations. In their digital universes, the signal is not rare at all. It is just another lucky roll. This is the grinding, technical heart of the conflict. It is not about who has the better telescope, but who has the more complete statistical model. The dark flow exists in this limbo of probability, its reality hanging on the decimal points of a p-value. To accept it is to say our standard cosmic model is missing a crucial ingredient. To dismiss it is to declare that we witnessed a 1 in 1,000 cosmic lottery win, a statistical mirage on the grandest possible scale. Every published paper is a new volley in this numbers war, each one claiming a more refined simulation or a cleaner data analysis. The mystery, therefore, is not just out in the cosmos, it is in the very process of how we know what we know, a reminder that at the frontier of science, truth is not simply observed, it is statistically convicted. The statistical war over the dark flow's reality has one inevitable outcome, a demand for better evidence. This 20th mystery shifts our gaze from the past to the future, from the data we have to the data we must collect. The resolution will not come from reanalyzing the same maps, but from building entirely new eyes to see the universe. A new generation of space observatories and ground-based experiments is now preparing for launch, each designed to probe the cosmos with a precision that makes our current tools seem primitive. Their primary targets may be dark energy or the infant universe, but they will also inevitably turn their gaze toward the mystery of the cosmic current. The European Space Agency's Euclid mission is already in space, beginning its ambitious 6-year survey. Euclid is not a microwave telescope. It is an optical and near-infrared observatory designed to create the largest, most accurate 3-dimensional map of the universe ever made. It will chart the positions and shapes of billions of galaxies across 10 billion years of cosmic history. This is crucial because the dark flow is not just about speed, it is about coherence across space and time. Euclid's exquisitely detailed map will allow astronomers to measure the peculiar velocities of galaxies and clusters with far greater statistical power, tracing subtle streams of motion across the cosmic web. If the dark flow is real, its signature should emerge from this monumental dataset as a clear, undeniable pattern etched across the vast canvas of the cosmos. Following close behind is NAS, a Nancy Grace Roman Space Telescope. With a field of view 100 times larger than the Hubble Space Telescopes, Roman will perform gargantuan surveys of the sky, measuring the distances to millions of galaxies and mapping the distribution of dark matter through the subtle warping of light known as weak gravitational lensing. This will give us an unprecedented view of the large-scale gravitational landscape. We will see not just where the matter is, but how it is moving in response to the total gravitational field, including any potential pull from beyond our horizon. Roman could effectively weigh the invisible attractor or prove its absence by revealing whether the observed motions of galaxies match the gravity of the visible mass alone. The most direct assault on the mystery, however, will come from the next generation of cosmic microwave background experiments. Projects like CMBS-4, a colossal array of telescopes planned for the high desert of Chile and the South Pole, represent a quantum leap in sensitivity. Where Planck detected temperature variations in millionths of a degree, CMBS-4 will measure them in billionths. It will map the polarization of the ancient light with such fidelity that it can isolate the kinetic Sunyaev-Zeldovich effect from distant galaxy clusters with near-perfect clarity, stripping away the confounding foregrounds that have fueled the debate. This is like moving from listening to a faint radio broadcast in a storm to hearing it in a soundproof room. These missions, working in concert, will perform a kind of cosmic triangulation. Euclid and Roman will map the present-day motion and mass distribution in stunning detail. CMBS-4 will use the pristine backdrop of the early universe to measure those motions independently, providing a cross-check of unimaginable precision. Together, they will either confirm the dark flow as a fundamental feature of our cosmos, pinpoint its exact scale and source, or finally reveal it as a complex illusion born from the limitations of our earlier instruments. Within the next decade, the whispering debate that has spanned years could be settled by the clear, unambiguous voice of new data. We stand on the threshold of knowing whether the universe truly has a current, and if so, where that river is ultimately trying to take us. A scientific debate over statistical noise rarely makes headlines, but the dark flow did. This 21st mystery unfolds not in the depths of space, but in the human mind. Why did this arcane cosmological puzzle, buried in datasets and theoretical papers, capture the public imagination so powerfully? The answer lies in its perfect, haunting simplicity. The core idea is instantly graspable. Everything we can see is drifting toward something we cannot. It takes the vast, abstract cosmos and gives it a narrative direction, a current, a flow. This transforms the universe from a static backdrop into a dynamic character with a will of its own, moving with purpose toward a hidden destination. That narrative proved irresistible. Documentaries featured dramatic animations of galaxy clusters streaming like leaves on a river. Science magazines ran cover stories with titles asking what lies beyond the edge of the universe. Online forums buzzed with speculation, weaving the dark flow into theories about ancient aliens, cosmic prophecies, and hidden dimensions. It became a staple of science communication because it bridges two worlds. On one hand, it is grounded in the tangible, physical reality of motion. We all understand what it means to be pulled. On the other, it points directly into the void of the profoundly unknown, invoking the ultimate mystery of what, if anything, exists beyond the limits of reality itself. This tension taps into a deep, almost primal human desire. We are pattern-seeking creatures wired to find meaning in chaos, to see faces in clouds and constellations in stars. The dark flow presents the ultimate pattern, a signature written across the entire sky, suggesting a design so immense we can only perceive its faintest outline. It promises that the cosmos is not random, that even its most colossal structures are part of a larger, ordered story. In a universe increasingly explained by impersonal forces like dark energy and quantum fluctuations, the flow reintroduces a hint of cosmic geography, a potential compass pointing toward a true somewhere. This resonance reveals something beautiful about our place in the cosmos. We are not passive observers, we are storytellers, and the dark flow offers a story where the ending is not yet written, where the final chapter might involve realms beyond imagination. It allows everyone, not just astronomers, to look up at the night sky and wonder not just what is out there, but where we are all going. That public fascination with a cosmic story reveals a deeper truth about our quest for understanding. The 22nd mystery of the dark flow is not about galaxies or gravity. It is a masterclass in the scientific method itself, a real-time case study of how humanity grapples with an extraordinary claim. The journey began with a startling announcement, a moment of genuine excitement that rippled through the cosmology community. Here was a potential discovery that could rewrite textbooks, a signal so profound it pointed beyond reality itself. The initial reaction was a mix of awe and intense scrutiny, as is proper. Then came the rigorous criticism, the deep and necessary dive into the data. Other teams reanalyzed the numbers, proposed alternative explanations, and pointed to potential systematic errors. The debate grew heated at times, unfolding in academic journals and conference halls, a slow-motion tug of war over the meaning of a whisper. This phase is not a sign of failure but of health. It is the immune system of science at work, attacking any claim that cannot defend itself with overwhelming evidence. The dark flow, with its faint signal at the edge of detection, proved a formidable opponent. It refused to be easily dismissed, yet it also resisted clear confirmation. This has led to our current state, a cautious, productive uncertainty. No consensus declares it definitively real or illusory. Instead, the mystery persists as an open question, a driving force for better instruments and sharper theories. This entire process, from bold announcement to skeptical grilling to unresolved tension, is often messy and frustratingly slow, but it is the greatest strength of the scientific endeavor. It protects us from the seduction of a beautiful story untethered from fact. The dark flow teaches us that the path to knowledge is not a straight line from question to answer. It is a winding road through a landscape of doubt, debate, and repeated testing. The mystery, therefore, expands. It is no longer just about where the universe is flowing. It is about how we, as curious beings, navigate the vast and often ambiguous currents of evidence, learning to distinguish between what we hope is true and what the cosmos is actually trying to tell us. The idea of a multiverse is no longer confined to philosophy or science fiction. It has become a rigorous mathematical framework within modern cosmology, and the dark flow sits at the very edge where this framework might meet reality. One of the most compelling models is eternal inflation, a vision of a cosmos in a state of endless, exponential expansion. In this seething quantum foam, pockets of space can randomly drop out of this hyper-expansion, settling into a more stable state. Each of these pockets becomes a separate universe, bubbling up like a foam in an infinite, boiling sea. Our entire observable cosmos is just one such bubble. For decades, this was a beautiful but untestable idea. How could we ever know about other bubbles when by definition they are causally disconnected from our own, separated by regions of space expanding faster than light? The dark flow offers a tantalizing, if speculative, answer. The walls of our bubble universe might not be perfect. During the nucleation process, as our bubble formed and expanded, it could have collided or brushed against a neighboring bubble in the higher dimensional bulk. That collision would have imparted energy, momentum, and direction to our newborn cosmos. It would have given our universe a gentle shove, a permanent tilt in its very fabric. The coherent motion of galaxy clusters we call the dark flow could be the lingering momentum from that primordial nudge, a fossilized directionality pointing back to the site of that long-ago contact with another reality. This transforms the multiverse from a philosophical speculation into a potentially testable scientific theory. We would not need to see the other bubble. We would only need to detect its gravitational wake, like feeling the breeze from a passing ship we cannot see in the fog. The dark flow, if confirmed, becomes that breeze. It would be the first empirical clue that our universe is not alone, that our physics is merely local bylaws in a much wider cosmic federation. The implications are staggering. It suggests that the fundamental constants of our universe, the strength of gravity, the mass of an electron, might not be finely tuned miracles, but simply the random outcome of which bubble we happen to inhabit. Our entire reality would carry within it the silent, directional signature of its birth among neighbors. The shape of space itself might be the source of the river. Our 24th mystery asks if the dark flow is not a current toward something, but an illusion created by the architecture of our cosmic home. We instinctively picture the universe as an infinite, flat expanse, a three-dimensional grid stretching forever in all directions. But what if it is not? What if the universe, while unimaginably vast, is finite and has a shape, a topology, like the surface of a sphere or a donut, but in 3 dimensions? This concept is called cosmic topology. One of the most studied shapes is the 3 torus. Imagine a cube where each face is magically connected to the opposite face. If you fly out of the right side, you instantly re-enter from the left. Go out the top, you come in from the bottom. This creates a finite, closed universe with no edges, a cosmic hall of mirrors. In such a space, light does not travel forever. It wraps around. A galaxy cluster on the far side of this folded cosmos could have its light reach us from 2 different directions, appearing as 2 identical ghost images on opposite sides of the sky. More crucially for our mystery, the large-scale structure of the universe would also wrap. The gravitational influence of a massive supercluster would not just pull matter in one direction within our local view. Its pull would echo around the closed loops of the topology, potentially creating the appearance of a coherent, large-scale flow in one dominant direction as the fabric of space itself is subtly tilted by these repeating gravitational patterns. The dark flow would not be a pull from beyond the horizon, but a looping current within a smaller, folded cosmos. This idea transforms the search. Astronomers hunting for a non-trivial topology look for its fingerprints in the cosmic microwave background. They search for matching circles, pairs of rings in the ancient light that show identical patterns of hot and cold spots. These would be the signature of the universe wrapping around on itself, like finding the same wallpaper pattern meeting at the seams of a room. If such circles were found, and if the axis of the proposed dark flow aligned neatly with one of the fundamental axes of this cosmic shape, it would be powerful evidence that the flow is an artifact of topology, a grand optical illusion of gravity and light on a cosmic scale. So far, exhaustive searches of the Planck satellite data have found no convincing evidence for these matching circles, suggesting if the universe is multiply connected, it must be larger than our observable horizon. But the possibility remains a tantalizing alternative. It elegantly eliminates the need for mysterious external attractors or collisions with other universes. Instead, the greatest mystery of motion might be solved by a twist in the geometry of everything, a final turn in the road that brings us right back to where we started, forever flowing within the closed curves of a finite reality. Our final mystery is not one of physics but of meaning. After 24 puzzles that stretch from the quantum foam to the cosmic horizon, we are left with the ultimate question. What does the dark flow truly tell us about the story of the universe? Whether it is a gravitational echo from another cosmos, a fossil from a previous cycle, or a statistical mirage, its very existence as a persistent question has already rewritten the narrative. It tells us that our cosmic tale is far from complete. The standard story of a smooth, isotropic universe born from a single Big Bang and expanding uniformly under dark energy is a powerful framework, but it may be just the first chapter or a single volume in an infinite library. The dark flow is the footnote that suggests there are entire paragraphs missing, plot threads that lead off the edge of the page. It points to a cosmos that is not just vast, but deeply interconnected in ways we are only beginning to sense, where the motion of a galaxy cluster here might be dictated by events in a realm we can never observe. This transforms our understanding from a static map to a dynamic, flowing system, a universe with currents and tides that hint at a geography larger than reality itself. The pursuit of this mystery has revealed something more beautiful than any single answer. It has shown that the universe, in its deepest silence, is still speaking. It whispers through the aligned motion of distant giants, through the cold spots on ancient light, through the statistical tensions in our data. These whispers do not give us solutions. They give us better, more profound questions. They invite us to imagine a reality that is stranger, more layered, and more wondrous than the one we thought we inhabited. The dark flow, in the end, may be less about a destination and more about the journey of discovery. It reminds us that the greatest gift of science is not the comfort of certainty, but the thrilling, humbling, and endless expansion of wonder. This river of galaxies, from its first faint signal to the dizzying possibilities it unveils, charts a journey through the very limits of human knowledge. We began with a simple, impossible motion, thousands of clusters streaming as one. That single anomaly unraveled into a tapestry of 25 interlocking mysteries, each one pulling us deeper into the unknown. We have confronted phantom masses beyond the horizon, questioned the foundational symmetry of the cosmos, and weighed the whispers of other universes against the cold statistics of error. We have seen how this one phenomenon challenges dark energy, invites quantum gravity into the light, and transforms our cosmic home from an island into a province of something infinitely larger. The cosmic dark flow is not merely an unsolved puzzle. It is a potential fault line running through the entire edifice of modern cosmology. If real, it signifies that our standard model, for all its stunning success, is incomplete. It tells us that the universe we think we know might be just a local chapter in a story whose full scope is written in dimensions and directions we are only beginning to sense. So the next time you stand beneath a clear night sky, look up with that knowledge. The darkness between the stars is not empty stillness. It may be a current flowing with purpose toward a destination hidden even from our most powerful telescopes. Let that feeling of wonder be your guide, for the greatest adventures in understanding do not end with answers. They begin with a single, unexplained motion in the dark, a whisper that reminds us the cosmos is stranger, more connected, and more alive with mystery than we ever dared to dream.